Hey, everybody. It's Monday, November 2nd. And as you can see here in the aim today, our main focus for this video is to talk about how we can describe how interactions between two objects affect the motion of objects. And essentially, this is really the point of Newton's laws, right? Is talking about how objects and the interactions between objects ultimately will affect how they move. It's essentially what the focus of dynamics is. We spent the whole beginning of the year talking about how objects were moving without talking about why they're moving. And so, to basically finish up the discussion about just the basics of Newton's laws of motion, we are going to talk about Newton's third law. Now, in this aim, the way that it's worded, ultimately, we already have what I'm going to write down here as like the first big note for today, which is that a force is an interaction between two objects. And so as a result, it is impossible for an object to exert a force on itself. This is a super, super, super important idea. It seems basic, but it ends up having big ramifications for how objects interact with each other. Now, every single time I put this up on the board in class, usually there's somebody who raises their hand and says, like, well, wait a second, I can exert a force on myself. And they like take their hand and they put it into their side and they push on their side or like push on their stomach. And they say, like, I'm exerting a force on myself. That's not exactly what we mean. What we mean is if an object could exert a force on itself, it could make that object accelerate. And that's not possible. So imagine the easiest way to sort of articulate what we mean here is imagine yourself standing on a skateboard. If you took your arm and pushed it into your side, let's just forget how big that is. If you took your arm and pushed it into your side, it would not make you roll on the skateboard. The only way that you could get the skateboard to move is to interact with something else, either by putting your foot on the ground or by using your hands to push off of a wall or something like that. And so the main idea here is that objects cannot exert forces on themselves to cause motion. They have to interact with other objects. And the whole thing about causing motion is not really necessary because we already know that forces would cause an acceleration. And so the key idea here is that if this distinction between whether it causes motion or not is tripping you up, it's important to realize the force should cause an acceleration. If you push into your side, you're not exerting a force on yourself. And if you don't quite understand why that's the case, then hopefully we'll be able to clear that up by talking about Newton's third law here today. This is very important, though, so take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, so a very common example of Newton's third law is a hammer hitting a nail. And as you can see here from the diagram, essentially what this diagram is showing is that the hammer hits the nail and the nail hits the hammer. Now, you guys already took physics, so I'm sure you remember what Newton's third law is, but we should just take a moment to ask a couple of basic questions here before we really get into the details. Essentially, what Newton's third law says is every action has an equal and opposite reaction, right? So what we're saying here is that when you take the hammer and you drive it towards the nail, when the hammer strikes the hammer exerts a force on the nail, and the nail exerts a force on the hammer. And so the obvious question that we have to ask here is, well, how do we know that the nail experiences a force? How do we know that the nail experiences a force? And it's because when the hammer strikes the nail the nail is going to move this way. And so the nail accelerates from rest. And since forces cause accelerations, the fact that the nail was at rest, sitting there, and then began to accelerate means that the nail certainly experienced a force. And of course, that begs the other question. Well, how do we know then that the hammer experienced a force? And all we really need to do, just like we did for the nail, is consider the motion of the hammer. The hammer is moving. And then when it strikes the nail, it either slows down a little bit, slows down completely, or slows down so much it stops and then accelerates in the opposite direction. Sometimes you can hit something so hard that it actually bounces back up. And so what we can say here is that the hammer slows down, stops, and even reverses direction. And so because both of these objects we know experience an acceleration, then we know for sure that these objects have a force acting on them. And so to describe Newton's third law, we can do it in a very useful way, or we could do it in a less useful way. So I want to talk about some definitions here. Newton's third law, as you'll almost always hear it, even as you heard it probably in middle school, is that for every action, there is an equal and opposite reaction. That, in my opinion, is not that helpful because it's not that clear as to what is actually happening. So the version of Newton's third law that's written this way is a little vague. And what we would like is a version of Newton's third law that is a little more detailed and specific. And so to put a little more detail on it in terms of exactly how it is affecting the motion of all of these objects here, we can say Newton's third law of motion says whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. And this is always true. Now, what's especially nice about being in school when we're doing this, and unfortunately, we're not, is that I can show you this right in front of your eyes. Now, I already have so far this year videotaped a demonstration for you, or at least a lab demonstration in the school. But because tomorrow is election day, I am not going to be at the school until November 10th. The next time I will be at school is November 10th. And so I will videotape the thing I would have showed you in class then. But until then, you'll just have to rely on my description of it. So in school, a few years ago, I convinced the school to purchase some very fancy carts. If you took honors physics with me, you might have seen it. And we have a track that these carts sit on. And because of the materials that the cart and the track are made of, it's essentially a very low friction cart. So you can roll this thing, like give it a little push, and it will roll at a constant velocity pretty much the whole way. It'll slow down a teeny little bit, but it'll roll at a constant velocity for like the vast majority of the time. And so what I do is there's like a little hole on the top where you can screw a post into. So I screw the post into the carts and I attach what is known as a force sensor on these carts. And essentially what the force sensor is it's just a box that has this like little nubbin on the end. And that little nubbin is covered in rubber, and it basically just like when it pushes into objects, it registers the size of the force that is exerted on the force sensor. And so what we see with this demonstration is that whenever I take the carts, no matter what the speed of the carts are, no matter what the masses of the carts are. What we see is that when we produce a graph of the force versus the time, and let's just say this is cart A and this is cart B, what we see is that the line for A may look like this, and the line for B always looks like that, like the mirror image within experimental error. And what I always think is pretty cool about this is that if you go to any particular point, which you can do with this tool, as I'll eventually show you, they'll always show you, and this part isn't particularly well drawn, but they'll always show you more or less, at least at two significant figures, that the forces are the same size, but with the opposite sign. And that's pretty cool to be able to see it in real life. Now, unfortunately, because you are not able to actually witness it in front of your eyes in the classroom, we could at least look at a good example in a real world context. Okay, so in this video, there are two astronauts aboard the International Space Station. And what they are demonstrating is how Newton's third law of motion works. And so this astronaut curls himself up into a ball and he's about to push on the astronaut in front of him. And notice when he pushes on the astronaut, this astronaut goes this way and this astronaut goes this way. And if you have to ask yourself the question, well, how does this astronaut, we'll call that astronaut 1, so how does astronaut 1 experience an acceleration this way, and astronaut 2 experience an acceleration this way? Well, it's because those astronauts had forces on them exerted in those directions. And so this astronaut had a force F2, and this astronaut had a force F1. And if we had a force sensor connected to the back of this astronaut over here and the hands of this astronaut here, what you would see is that the forces measured by those force sensors would be exactly the same. And so just to play it back one more time, they start together, they push off of each other, and then they fly away. And notice this graphic was essentially showing you what I was just showing you there. We see the force, the action, and then we see the reaction. Now, the reason why I don't like the first formulation of Newton's third law, for every action there is an equal and opposite reaction, is because it loses some of the important detail, I think. So what we should say here is that while it is true that every action has an equal and opposite reaction, it's important to remember the action and the reaction are acting on different objects, and that the action and the reaction take place only between the two objects. Now, this essentially goes back to why you can't exert a force on yourself, because even though your hand is a separate part of your body than your side, when you push on your side pushes back on your hand, and the net force on your body is 0. And that's why if you were standing atop a skateboard and you just pushed into your side, you wouldn't end up moving. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, now a second ago, I said the reason why I don't like this first formulation of Newton's third law is because I think it loses out on some of the details. And these details here, that there are two objects involved, is a really, really super important point. And so I'd want to take a minute or two to just like really dive into the weeds here on this one. So the first thing that we should say here, and all of this should be written under the heading action-reaction pairs, is that Newton's third law tells us that all interactions occur between two objects. So there really is no such thing as a force. Now that sounds like a really weird thing to say, but since interactions are between two objects, there really is no such thing as a force or a single force. because since interactions always occur between two objects, and each object exerts a force on the other object, all interactions result in two forces. So the fact that Newton's third law basically guarantees that all forces are interactions between two objects, and so really there's always two forces whenever objects experience an interaction. We need to be very mindful of these two forces because the two forces are very important and they get a very specific name. They are referred to as being part of an action-reaction pair. So an action-reaction pair is the name we give to the equal and opposite forces that arise from Newton's third law. And so now we have a very big issue to address, because if every interaction results in two forces, and those forces are always equal and opposite, then why don't the action-reaction pairs cancel out? Right? We said here that when you have two forces and they're equal in size and opposite in direction, to combine vectors, you add them with the sign. And when you add vectors with the opposite signs that have the same size, they should cancel, right? Why don't they? Take a second to pause this video here and think about that, because this is a really important point. So the answer to the question, why don't the action-reaction pairs cancel out, is actually pretty simple. The action-reaction pairs don't cancel each other out because the action-reaction forces act on different objects. I hope everybody realizes that what we are seeing here are two fundamentally different situations. When we're talking about this, a case where we have one object with two forces acting on it, which are equal in size, but opposite in direction, versus whether we have a situation like this, and this object has a force acting on it like this, and this object has a force acting on it like this. Because you cannot add forces with the signs for two separate objects. Because when you sum forces together by using any of those equations, you have to talk about the forces that are acting on each object in particular. And so in this context, down here, Newton's third law is probably best stated by saying the force that object 1 exerts on object 2 is equal to the negative of the force object 2 exerts on object 1. Take a second to pause this video here and write that down, and when you hit play, we'll move on. And with that, now we're pretty much ready to get into questions on a sheet that I've attached to the post on Google Classroom for today. So if you take a look at the Google Classroom page today, you will see two sheets. One of them is called Newton's Third Law Worksheet number 1. The other one is called Newton's Third Law Worksheet number 2. And so to start this one off, I'd like to take a look at the first problem, WWT 55. B3 WWT 55. It says, a tennis player returns a serve. A physics student watching the match makes the following contention. While the tennis ball is in contact with the tennis racket, the racket exerts a larger force on the tennis ball than the tennis ball does on the racket, because the racket has to stop the tennis ball and then reverse its motion. What, if anything, is wrong with this contention? And if something is wrong, explain the error and how to correct it. If this contention is correct, explain why. I'd like you to take a couple minutes, like let's say 4 minutes, pause this video, and go ahead and answer this question. I want you to write an explanation. I want you to address specifically two things. I want you to address head-on what the kid says, and I also want you to address head-on how principles of physics apply to this problem. And when you hit play, we'll go over it. Okay, so in this problem here, essentially what this kid is saying is that the tennis racket has to cause the tennis ball to slow down, then stop, and then reverse its motion. So essentially what the kid is saying is that because this tennis ball has to experience this huge acceleration because it's being slowed down, stopped, and then turned around, it has to be experiencing a larger force because it's experiencing a larger acceleration. It sounds fairly compelling, larger force, larger acceleration. But of course, there's one thing that the kid is forgetting. And so what we can say here is this student is certainly wrong. According to Newton's third law, the force that the tennis ball exerts on the racket is equal to the force the racket exerts on the ball. Of course, they're in opposite directions. The only reason the ball accelerates more than the racket is because even though both objects experience the same force, the smaller mass of the ball yields a larger acceleration. Take a second to pause this video here and write that down, or amend your explanation to add whatever may have been missing from your explanation. And when you hit play, we'll write a note about that. So, this question brings up a very important issue with these questions, because they're always going to address this misconception that kids have that just because something is bigger or smaller or accelerates more or accelerates less, then that means the force must be different. Forces, or I should say, we can say it both ways. Force depends on mass and acceleration, or put another way, the acceleration depends on both the force and the mass. So essentially what we're saying here is when two objects are interacting and exerting equal size forces on each other, they don't have to experience the same acceleration. And this is because the two objects might have a different mass, but also because both objects might have additional forces acting on them too. And so this is generally shown here with an equation that you can write that looks something like this. So we can say F net 1 equals F net 2. And usually what people write is they write like a bigger M, and then they'll write a small a, and then they'll write a small m, and a big A to sort of get the point across here, that the product of M and A need to be big. So if the mass is big, the acceleration will be small. And for an object with a small mass, well, then it'll have a big acceleration. Take a second to pause this video here and write that down. And when you push play, we'll move on. I want to take a second to address this because both objects might have additional forces acting on them business. So this actually comes up, we're going to skip this one because it's almost identical. This comes up in this next question here. So in WWT 56, it says ball hitting a wall, forces. In this situation, the wall exerts a larger force on the ball than the ball exerts on the wall. This is when this person just throws the ball at the wall. And it's the same kind of situation, the ball rebounds. So it experiences a big acceleration. And they say that is the ball goes from an initial speed to 0 and then from 0 to the rebound speed. But the wall does not accelerate because it's stationary the whole time. And what they're using that evidence for, like, it's important to realize that's a fact. The ball accelerates a lot. The wall doesn't accelerate at all. But what the student is trying to do is use that as evidence for why the wall exerts a larger force on the ball than the ball exerts on the wall. The whole idea, though, behind this one is that the wall is connected to other parts of the building. And so because the wall is connected to other things, there are other forces exerted on the wall besides the force from the ball that prevent the wall from moving. That's the idea. And so what I wrote here is this student is wrong according to Newton. It's basically the same thing. According to Newton's third law, the force the ball exerts on the wall is equal to the force the wall exerts on the ball. The ball only accelerates more than the wall because the ball, although it experiences the same force as the wall, has a significantly smaller mass, which causes it to experience a larger acceleration notice here that's not really the whole thing. It's also because the wall has an additional force or additional forces exerted on it from all the nails that it's attached to, and the beams it's attached to, and the floor. And so basically, what you really need to pay attention to in these problems is which objects are exerting forces on each other. Because essentially, like Newton's third law is very easy. It just says the force from one object on another is equal to the force from that object back on the first object. It's pretty simple. But they're always going to try to give you scenarios where they're trying to trick you. So let's take a look at another example. This example says here, it's B3CT54. It says two toy trucks traveling at different constant speeds are about to collide. The two identical trucks are traveling in the same direction, and truck B is carrying a heavy load. During the collision, will the magnitude of the acceleration of truck A be greater than, less than, or equal to the magnitude of the acceleration of truck B? I'd like you to take a couple minutes to pause this video here and answer this question, write up your explanation, and when you hit play, we'll go ahead and go over the answer. Okay, so I like these problems. And what I like about these problems is that these are problems which force you to use more than one of Newton's three laws at a time. And so it really is like a nice sort of synthesis question. And so really what you need to ask yourself is like, well, what do the laws tell me about this particular problem? And so the first thing that we should ask, obviously based on what we're talking about today, but also because there are two objects involved, is what does Newton's third law tell us about this situation? Now, before we do that, though, I just want to take a second to address the thing that I just said. I feel like what I always see every single year is that when we are spending time in class talking about Newton's third law, everybody has like their sort of Newton's third law radar on high alert. And like, you know that the answer, because we're talking about Newton's third law today, is going to have something to do with Newton's third law. But then when we leave the class and we see these problems in the future, people are like sort of unsure about when to apply it. Whenever you see multiple objects interacting with one another, which always has to be the case, whenever objects are interacting with each other, Newton's third law applies. So you should recognize immediately, well, there are two trucks here. These trucks are going to interact with each other. And so truck A is going to exert a force on truck B in this direction. So this is the force on truck B exerted by A. And truck B is going to exert a force on A back this way. And so this is the force from A on B. And what Newton's third law says is FAB is equal and opposite FBA. So these objects certainly experience the same force. But of course, that does not mean the answer is 3 equal to, because they're not asking about the force, they're asking about the acceleration. And you have multiple options here. Your first option, which is probably the most obvious, is just to use Newton's second law and talk about the relationships. And so the question here says, during the collision, will the magnitude of the acceleration of truck A be greater than, less than, or equal to the magnitude of the acceleration of truck B? Notice truck B is the one with this big heavy load on the back. And so this one has the bigger mass. And so what you can say here is that the acceleration is inversely proportional to the mass. I feel like we haven't talked about this in a while, so just to remind everybody, there is no symbol for inversely proportional. So essentially what you just have to say is A is directly proportional to the inverse of the mass, at least with the symbols. Obviously, when you're using your words, just say inversely proportional, but that's the idea. So the answer to the question looks a little something like this then. According to Newton's third law, both trucks will experience equal and opposite forces. According to Newton's second law, for objects experiencing the same net force, a smaller mass, object A, will experience a larger acceleration, since acceleration is inversely proportional to mass. As a result, object A has a larger acceleration than object B. And so that makes the answer 1. Take a second to pause this video here and write that down, or amend your explanation, including anything you may have missed, and then we'll move on. The important thing to recognize about this question, I think, is that you have to realize that this is not the only way to answer the question. Because while Newton's second law is a perfectly viable way of answering this question, at least as far as the acceleration part is concerned, after you've addressed the forces part, you can also use Newton's first law. What Newton's first law says is that an object with more inertia is going to resist acceleration more. And so because mass is a measurement of inertia, you could also say, according to Newton's first law, an object with more mass has more inertia, which means it has more resistance to acceleration. So since object A has less inertia, it resists the acceleration caused by those same size forces less, which means it's going to accelerate more. So every time, and you're going to see these problems a heck of a lot, every time you have to apply more than one of Newton's 3 laws, generally you're going to have to apply the third law to talk about the size of the force, and then either the first or second law to talk about the acceleration. And because that's a very important point, I think it's probably worthwhile to take a moment to write that down. And so we'll say, generally, and this isn't always true, but generally, since the first and second law say the same thing, when you're tasked with using 2 of Newton's laws to describe the motion of an object, you can use Newton's third law in conjunction with either Newton's first or second law. That's the idea. The third law says something different, but the first and second law essentially say the same thing. Take a second to pause this video here and write that down, and when you hit play, we'll move on to the last question on that sheet. So for the last question on that sheet, I think what you'll see is that it says here we've got these 2 identical trucks, but now they're traveling in opposite directions. And they're asking us to determine how the acceleration of A compares to the acceleration of B. And I hope everybody realizes it doesn't matter. Because according to Newton's third law, no matter what, the forces are the same. And so really all I want to do for this one is just to acknowledge that although this is a slight variation because they've switched the direction of the truck, it's essentially the same problem. And what we should say about this one is, note, the action-reaction pairs produced between 2 interacting objects have nothing to do with the object's masses, initial velocities, or final velocities. The forces will always be equal and opposite. And then the last point here would be only the acceleration is affected by the masses. It is affected by nothing else. The only real difference between these 2 situations, the one where we had those trucks moving in opposite directions, was the initial speed, so it doesn't matter. Take a second to pause this video here and write that down. When you hit play, we'll move on. So now I actually want to go ahead and answer that question because I just almost posed it and didn't. What do you think the difference between these 2 problems is? In the first case, you have this first truck A, moving 4 meters per second to the right, and truck B moving 3 meters per second to the right. And in the second case, we have truck A moving at 3 meters per second to the right, and truck B moving at 4 meters per second to the left. What's the difference? Well, obviously the difference here is the initial velocities of the objects. And so based on whatever the acceleration is going to be, the objects will have different final velocities. Because like if you had the same acceleration in two cases and your initial velocity was different in those cases, obviously the final velocity would be different. It's also important to note here, what is going to be different is the size of the force. Now, I want to be very clear about what I'm saying. The size of the force that both objects experience in this case is going to be different than the size of the force that both objects experience in that case. In both cases, both objects experience the same size force. Object A experiences the same size force as object B. But between the two situations, the fact that this object is only going 1 meter per second faster than this object, object B, means that they're only going to bump slightly. It's going to be like a gentle tap. But the fact that these objects are going head on now, and instead of having their relative velocity here just be 1, the fact that the relative velocity is 7 means that these objects are going to exert quite large forces on each other. But regardless, both objects will experience the same size force, no matter what the size of that force actually is. If we took these objects and made them move at 300 meters per second and 400 meters per second, obviously the force that they would experience would be bigger, but they would each still experience the same size force. And that's a very important point. And with that, that's really it for that sheet. And so the main thing to realize when you're looking at questions like these, again, is when they're asking you to find or to compare accelerations, you have to use Newton's third law to establish that the forces are the same. And then you're going to use one of Newton's other laws to talk about the accelerations. And this was something that we wrote down in class last year, which I thought was pretty funny when I saw it, so I figured I'd show it to you. The forces are always the same. That's a crucial idea. It doesn't matter. Don't fall for the tricks. In AP physics, the tricks are pretty tricky. And you'll see that as we go through and practice problems. So now that we've talked about yesterday, or sorry, not yesterday, Friday, now that we talked about weight, and today we've talked about Newton's third law, we're ready to talk about the normal force, if you remember this from honors physics. So the first thing we want to ask here is, I want to ask you to consider this book. What kind of motion is being experienced by this book? This book is at rest. So the speed of the book is 0. And I'm going to write that down over here. The speed of the book is 0. And if the speed of the book is 0, and it's always going to be 0, because the book is just sitting there, then what does that tell us about the acceleration of the book? Well, it tells us the acceleration of the book is also 0. And now we have a very big question to ask. If the acceleration of the book is 0, what does that tell us about the book? And of course, because F net equals ma, if the acceleration of the book is 0, the net force is 0. But of course, as we mentioned yesterday, isn't there a force of gravity acting down on the book? Does the force of gravity just stop acting when an object is sitting on a table? No, of course not. That's absurd. So the only logical conclusion that we can draw here is that when the book is sitting on the table, because it has a downward force of gravity acting on it, but is not accelerating downward, that there must be some upward force acting on it, canceling out the force of gravity. And this force is called the normal force. So let's talk about the normal force for a second. So the first thing that we should say here is that when an object is sitting at rest on a surface, because it's at rest, we know the net force acting on the object must be equal to 0. And that's because it's at rest. The acceleration is 0. There's no net force. Secondly, since the net force acting on the object is 0, we know that there must be some upward force acting on the object to cancel out the force of gravity. I put cancel out in quotes there because I didn't want anybody to think that I meant like canceled means like it stopped acting. It just doesn't accelerate the object. And to tie that together here, we can say since the force of gravity acting on the object is causing the book to push into the table, or in other words, exert a downward force on the table exerts an equal and opposite force upward on the book. Take a second to pause this video here and write that down because these ideas are very important. Before we really define the normal force here, we just got to get a few definitions out of the way. The first definition is the definition of a contact force. Shocker, a contact force is a force that occurs when two objects are, you guessed it, in contact. And the normal force is an example of a contact force because it occurs when two objects are in contact. Before we define the normal force, we also want to define the word normal. And what we mean when we say normal, remember, is that normal is a mathematical term. And the word normal means perpendicular. And so in this context, when we use the phrase the normal force, normal is an adjective describing the force. And really what it's saying is just that the normal force is a force that acts perpendicular to the common surface of contact between two objects. What we should also probably say here is that it's the force exerted by the surface. So in the case of that book, it's the force exerted by the table. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And this part is exciting because now that you have all taken chemistry, you actually have some basis for understanding what the normal force actually is. As you learned in chemistry, I hope, is that every object is made of atoms. No, right? Obviously you knew that before, but what you should have learned in chemistry is that the way that electrons essentially organize themselves in atoms is that they form like these closed shells on the inside, and then on the outside what we have are what we refer to as valence electrons. And so because the atoms on the inside end up forming like these closed shells, you effectively have like not much of an effect from the net charge on the inside of these shells, but on the outside, in the valence band, what you see is that since you have just electrons, there's like a slight negative charge there on the outside due to these electrons. And so essentially what happens when you put an object on a surface is that the valence electrons in the atoms in the box get closer and closer and closer and closer to the valence electrons in the table. In this case, it's a box on a table. And of course, because electrons both have a negative charge, they repel each other. And so these valence electrons can only get so close before the force of repulsion is so large that they just can't get any closer Because, as you may remember from honors physics, although maybe not because it was a while ago, the electrical force between objects, as described by Coulomb's law, says that the force gets way, way, way bigger when the objects get closer to each other. They're inversely proportional. The force is inversely proportional to the distance. So as this distance here shrinks between these valence electrons, the force gets so huge that eventually the object can't get any closer. It is important to realize that essentially what we're saying here is that the objects which to you look like they're touching are not actually touching. Their atoms do not come in contact. In that sense, no atoms ever really come in contact from two separate objects because the electrons can only get so close before the force of repulsion is so huge that they can't really touch, because if they touch, then this distance gets really, really close to zero. And if the distance gets really close to zero, the force of repulsion goes up toward infinity. And so essentially what we're saying here is that whenever you feel contact, like when I clap my hands right now, what I'm not feeling is my other hand. What I'm feeling is the force of repulsion from the electrons in my hand. Pretty cool. Okay, so the last thing we want to say here very quickly is that we can say something important about the normal force by drawing a little diagram here. And as you'll see this week, these diagrams are going to be very important. And so usually when we draw these diagrams, we just draw like a big dot at the center of the object. And so we have the force of gravity coming straight down. And we have the normal force coming straight up. And we label the normal force with the subscript F with the subscript N. And so what we can say here is that the sum of the forces equals ma, right, as always, but the acceleration is 0. So that means the sum of the forces equals 0. And when we have two forces that are acting in opposite directions, we subtract them. And so the normal force is going up, so we'll call that positive. And the gravitational force is coming down, so we'll call that negative. So we have the normal force minus the gravitational force, and that's equal to 0. And the only thing we can do with that equation is recognize something really, really important, which is that the normal force is equal to the gravitational force in magnitude. Right? These forces are equal in magnitude and opposite in direction. And that's a very important idea for a lot of the things we're going to be talking about here in this course. So take a second to write that down. This is a huge note. On a flat, horizontal surface, the normal force is always equal in magnitude to the weight, but acts in the opposite direction. Take a second to pause this video here and write that down, and when you hit play, we'll wrap it up for today. All right, guys, since the only other thing we really have to do with this is solve some problems, but this video is already getting to be a little long, we'll just go ahead and save that for tomorrow. So with that, that's it for today. Remember, as was posted last Friday, we're going to have a test on graphing on Friday. And so the homeworks this week, including the one that was due today, are going to be practice for that test. All right, everybody. Have a good one.